In this paper, we present fatigue crack paths in titanium alloy orthopedic plates. List of authors you can see at this slide. In the introduction, we want to emphasize three important issues and facts. The first one is a relatively frequent failure of these plates, orthopedic plates. I would even say surprisingly frequent failures. This was the driving force behind the research that we will present, which is basically a numerical one, because as the second issue that I want to emphasize, we investigated different orthopedic plate designs, and that was done with the focus on crack path issue. So that was accomplished by using of ANSYS, so commercial finite element software, and that is our third issue to be emphasized here in the introduction. Here you can see examples of failures of orthoplates. They are all fatigue in there as a mechanism of failure. So this is why we will investigate fatigue crack behavior. To start with, before we apply numerical methods, of course, we need to know some parameters, and then that will be accomplished through the standard testing, as you will see in the next two slides. Basic data about testing is shown in this slide. It was done according to ASTM standard E647. It was done in load control and under load ratio of 0.1 prescribed recommended frequency range. You can see here also measurement system, a sketch, which was based on indirect potential drop method to continuously indicate measurement values. So in this way we can record crack length, and by counting cycles we can get the curve which will provide us with the coefficients of Paris law. So this procedure was applied on titanium alloy typically used for orthopedic plates. 3 specimens were tested. Results are shown in form of diagram and also as results for coefficients C and M in Paris law, as well as there is also data for stress intensity factor threshold value as given in the table at the bottom of the slide. Now we can focus our attention to numerical simulation. It was done by using extended finite element method as embedded in ANSYS software. So we were able to simulate a fatigue crack growth. We chose 5 different plate geometries marked as A, B, C, D, and E, and you can see sketches and cross-sections of these plates on this slide. Loading was treated as for 4-point band testing with maximal moments corresponding to 60, 90, and 120 kilos of body weight. Characteristic points like supports and loading points are shown in the sketch below. Also, loading force for all 3 different body weights and 5 different plate types are given in table 3. Here we can see finite element meshes for plates A to B in this case, and then in the following slide for plates C, D, and E. A total of 60 steps of crack growth were set in ANSYS, and all data for meshes are given in the table top right. Details of finite element meshes are given in this slide, so you can see for all 5 plate types the initial cracks, and also you can see in more details geometry of the holes where cracks are positioned. These positions were determined according to the static stress analysis, so at the locations where the stress concentration were the highest. In this slide, we can see the final view of cracked plates. So once the crack propagated through the whole thickness, we get different views for these 5 plates as shown here. From the point of view of practical application of this research, we can see now 3 sets of diagrams. They are given for 3 different body weights and for all 5 different plate geometries. And of course the longest life is for body weight of 60 kilos. If you compare plate B in these 3 figures, you can see that almost 5 times is the ratio between 60 and 120 kilos, of course in favor of lighter body. And if we compare 60 and 90, then this plate D would have about 2.6 or 7 longer life for the lighter body. In this slide, we can see how crack propagates in the case of plate A, and also we can see that the numerical simulation quite well resembles the real crack propagation, which is shown in the figure at the bottom to the left. And also we can see that at the beginning, crack grows both at the surface and through the thickness, but then it starts dominantly to grow along the surface, and then once it went all the way to the surface, then it goes more into depth until the final failure. In the following 4 slides, one can see crack path grow through surface and thickness for plates B, C, D, and E. In all cases, there were about 6 characteristic numbers of cycles that were used for these illustrations, and one can notice some differences which are quite important. Now for the conclusions, we may say that after crack initiation, the remaining life of all plates under 3 different body weights is very much different. 80 or 60% shorter, for example, when we compare 120 and 90 with 60 kilos. Then we can conclude that differences in remaining life between compared plate geometries stay the same under different loading. And also we can notice that plate designed to provide less contact with bone surface has the shortest remaining life. So what we want to emphasize at the end of this presentation is the fact that crack propagation path is the most important aspect in this analysis. We can see that more than 2 mm longer than plate's thickness is something specific for all cases, because a crack stops propagating through thickness at one point and continues along plate surface. So in total, its path is not only longer, but also different. And as already said, this is the most important conclusion, and this has to be taken into consideration when designing the plates so that we get as long remaining life as possible.